Hello! In this lesson, we're going to talk about the fundamental building blocks that digital computers are made of. Now, there are also analog computers and mechanical computers, all kinds of different computers, but we're talking specifically about electronic digital computers because that is primarily what we use these days. Okay, you've probably heard of this guy. His name is George Boole. And back in 1847, he wrote a book called The Mathematical Analysis of Logic. A few years later, he also wrote another book. Basically, he defined a system that eventually came to be called Boolean algebra. Boolean algebra is a series of equations that let us work with logical constructs and manipulate them. There were many people who contributed to this. Now, you may not have heard of this guy. His name is Claude Shannon. And he actually played a really pivotal role because what he did is in 1937, he attended a philosophy class. George Boole's mathematical analysis of logic was being taught as philosophy, not being applied to electronic circuit design. It was Claude Shannon who took the philosophy class, and he came to the realization that, hey, wait, I can use this for designing electronic circuits. Well, at that time, electrical circuits. They were working with relays. But it wasn't very many years later that they started working with vacuum tubes and then transistors, things like that. So the first computer was indeed made out of mechanical gears. The next significant computer was made out of vacuum tubes. The next significant one was made out of relays, and then vacuum tubes, and then the transistors that we have now, and the microchips. So what do we mean when we say, let's clear this. What do we mean when we say digital logic? Well, digital logic consists of three fundamental gates. We have, get the right tool selected here. Okay, there we go. We have not. We have or. We have and. These three building blocks are what computers are constructed from. Believe it or not, everything that a computer does comes down to these three logical operations. Even more intriguing is that we can actually reduce this down to combinations of what's called a NAND gate. And we'll get into that later. But interestingly enough, you can create all these other gates out of a NAND gate, or combinations of a NAND gate. But that's really more for theoretical knowledge, and if you're actually designing the circuits, the low-level circuits of transistors, it's useful to know that. But otherwise, you don't need to worry about that. When we do computer programming, we are also making decisions based on the operations of not, or, and. There's also another gate that we use, and that is the XOR. Now the XOR, not the best drawing in the world, but I think you get the idea. Now the XOR is basically an OR gate, but it has an extra bar here, designating that it's an XOR. So that too is an important gate. But the XOR is actually constructed of a combination of ands and ors. So we're not going to worry too much about that just yet. What I really want to focus on are these three fundamentals here. Now, what do we mean when we say logic? Well, we're talking about prepositions, statements basically, that are either true. Hello? Uh-oh. Oops. Sorry. Hang on here. Still getting used to this system. Okay. Things are either true or they're false. So, if I make the assertion that it's raining outside, you would need to go look out the window, and then you could tell me it is raining or it isn't raining. Now, if I make the assertion that it's raining outside and you come back and say that it's not raining, then that assertion is false. But if I say that it's raining outside and you come back and tell me that it is raining outside, then that assertion is true. So this is a beginning of trying to approach the idea of how we use logic to model real-world scenarios. We'll keep working on that. I just want to give you an idea to begin with. Now, computers manipulate symbols, and we use symbols to represent concepts. If you took the lesson on binary, you'll see where I talked about the importance of concepts and how we're not actually working with numbers, we're working with concepts and symbols that represent those concepts. So here's a 1. Well, this is a squiggle that represents the concept of 1. And here's another squiggle, and this squiggle represents the concept of 0. So we associate the value of true with the number 1. We associate the value of false with the number 0. Okay, so now, circuit-wise, we associate 1 with has voltage. And we associate 0 with no volts. Now, the way that we can, hang on. Sorry about the interruption. My screen very abruptly decided to go for a walk, and it didn't bring me along. So, all right. So, the way we can represent this electronically is with a switch. And we'll just draw the switch like this. And we have our little light bulb, and there's a ground and power. So the light bulb is off when the switch is open because there's no current flowing through here. And the light bulb is on when the switch is closed. So we associate these two values. A closed switch is true. It's a 1. It has volts. An open switch is a 0. An open switch, there we go, open. Okay, switch is open. An open switch is false, which is 0, which is no volts. There's no current reaching the light bulb, therefore there's no voltage reaching the light bulb. Okay. So that is the basis that we use for our circuitry in the computer. Now let's talk about the individual gates. Start with OR. Here's our OR gate. Okay. The word OR in the English language, if you think about it, what does it really mean? We're saying that, well, let's make the assertion. I have a fruit. Okay. If I'm holding an apple, then I have a fruit. So that statement's true. If I have a pear, I'm also holding a fruit. So again, the statement is true. But if I'm holding some lettuce, then I'm not holding a fruit. So the statement's false. So if I'm holding either an apple or a pear or both of those things, my statement is true. We use a very valuable tool in logic. We use this thing called a truth table. And we can represent this in and out. Then I'm going to go, okay, let's label this. This is A, this is B, this is out. Put B here, put A here. So if I put a 0 on A, and I put a 0 on B, then I'm going to get a 0 out. So let's write that over here. So we put a 0 on A, put a 0 on B, we get a 0 output because 0 or 0 is 0. If I'm not holding an apple and I'm not holding a pear, then I'm not holding a fruit. So my output is false. My output is 0. Now, suppose that A is 1, is a true value. Or in this example, suppose I have an apple in my hand for A, for the input. Of course, you can't really use an apple as an input, but I have an electrical signal that represents the value of 1 or the value of true. Because 1 and true, we're using them both to mean the same thing. They're synonyms of each other. That gives us a 1 output. And we don't actually care what the value of B is. So let's put a 0 for B. Now, suppose that A is 0, but now B is a true input. Okay, so again, I have a 1 there, representing electrical voltage. And if B is a 1, then we don't care about the value of A. It doesn't actually matter. So the value of A doesn't really matter here. The value of B doesn't matter here. As long as we have a 1 in either of these columns, then we get a 1 output. And so, that being the case, then if we have 1 or a 1, we still get a 1 output. Okay. There are, I don't know, probably half a dozen different symbol systems that have been used to represent Boolean algebra and logic notation. I'm going to use the symbol that most computer languages use because I think that will be less confusing if we express this in terms of computer programming. So here we go. This is the symbol for the OR function, the logical OR. And these are two separate characters. We call them pipe characters. If you look above your Enter key, you'll see, well, it's above it or a little bit to the left of it, somewhere very near the Enter key. You'll see a key that has a, it's going to have a backslash on it. And then when you do the shift of the backslash, then you get the pipe character, which is a vertical bar. So that's what you hit in order to make a pipe. And you need two of them for a logical OR. Okay. All right. So that is our truth table. And this is the OR function. Now a little bit later, actually I guess in the next lesson, I'll show you how we actually use these gates to do something interesting with them, to actually achieve something useful with them. But before we can start talking about how we use the gates, we first have to learn what the gates do, what they are. So we have to know what our building blocks are before we can start using them to construct something. So I know it might seem a little abstract right now, but just note that we're going to get there. We will talk about how these components are actually used. But first we have to learn what the components are. Okay, let's talk about the inverter. This is the simplest of all gates. And it's normally drawn like this. We call it NOT. What it does is it inverts the input to the output. So if we go, if we put a 0 here, we get a 1 here. If we put a 1 here, we get a 0 there. And we can draw our truth table over here with our in and our out. And it looks like this: 0 in, 1 out, 1 in, 0 out. Okay. Now, the NOT is a little different in terms of, well, how would we represent it? So I think the simplest way to represent it is a push button. We're going to have a push button here. And the push button has a shaft here. And the shaft has this metal bar. And what the metal bar does is it makes a connection between these two wires. Now there's a spring. What the spring does is the spring is pushing up on the push button. And of course you have your light bulb over here. And okay, so what happens here is that when there's no pressure against the push button, this spring is pushing it up, and it's pushing the bar against these contacts, and it's in a closed position so that current can flow through the wire, applying the voltage to the light, turning it on. Okay. Now, when we push down on the button, exactly the opposite happens, because then what happens is that we're pushing the bar away from these contact points, and opening that connection, the light goes off. So that is the circuit for a NOT. That is the function of a NOT. It simply reverses whatever you have at the input. It gives you the opposite of that at the output. So if you put no volts at the input, you get a voltage at the output. If you put a voltage at the input, you get no volts at the output. Okay? Let's go back to the OR for a second. How would we portray this as a circuit? Well, it's basically two switches. I need some room to draw this. So let me just erase this guy real quick. Okay. There we go. Okay. So how we do this is we are running a switch here. That's one input. And we run a switch here. That's our other input. And then we take both of these and we run them to our lamp. And then we run both of these to our power. And there it is. So if I close this switch, then power can flow through the wire and light up the bulb. If I close this switch, then power can flow through the wire, light up the bulb. If I close both the switches, then the bulb lights up. If both of the switches are open, then the light bulb is off. And that's exactly what we see right here. We see both switches are 0, then the light is off. The output is 0. If one of those switches is turned on, or if both of those switches is turned on, doesn't matter which one, then the light bulb lights up. So that's our OR function, the OR gate. Okay. Now for the AND, which is also pretty simple. Let's see, that's supposed to be more rounded. The OR has a pointy, here, let me draw that better. The OR gate has a pointy top. The AND gate has a round top and a flat base. So the OR's has a curved base and a pointy top. The AND gate is a flat base and a round top. Okay. So there's our AND. And we have our A and our B and our out. So let's look at the truth table for an AND. Well, we have our in, out, B, A. So what do? We need to go through all possible combinations of A and B. So basically we're just counting. That's really what we're doing. So we go 0, 1. Now what's a binary 2? Well, 2 in binary is you put down a 0 and you carry 1. And then 3 is you just add another 1 to it. So we're going, and then we put leading zeros here just to make it clean and to have clarity of what the state is. So here's what we're doing. We're going 0, 1, 2, 3. And that takes us through all 4 possible combinations of inputs and outputs for 2-input gate. Okay. Now, and is that you have to have both things. Suppose you're going to go outside and it's raining out. So you need your hat and your coat before you can go outside. So that's the function of AND. If you don't have both of those things, then you don't go outside. So 0 and 0 is going to produce a 0. It's false. We can't go outside because we don't have either our hat or our coat here. 0 or 1. Well, we only have one item. Say that's the hat. But we don't have the coat. Well, we need both the hat and the coat, so it's 0 again. And 1 and 0, that's another 0 because, again, we have to have both of them. So the only time this is true is if 1 and 1 gives us our 1 output, our true output. So how would we draw the gate for this? Well, the gate, a circuit for this gate. a circuit's going to look like this. It's, again, we have our two switches. We have our A switch and our B switch. And we have our little lamp here. And our voltage in. So, here's what we do. If you close A, can current flow? No, because B is open. The circuit's not connected. If we close B, but B is open, can the current flow? No, because A is open, so it can't cross the gap. You have to close both of those switches in order to light up the light bulb. And that is how an AND is constructed. So you could do this directly as relays. Now, when we're doing transistors and such, it gets a little bit different, the actual internal circuitry of it. But if we were using relays, this is exactly what you would be looking at. You'd just put the relay coil down here, and it would look exactly like this diagram. Now, when you're doing silicon transistors and CMOS and such, well, that gets to be a whole other thing, but that's not the field that we're going to be looking at. We're looking at computer architecture itself at a high level, at an idealized logic level. That's what we're talking about. So we're not going to get involved in a lot of the messy stuff to do with the actual circuits. Okay, now, the symbol for AND in programming, I'll tell you what, let's go to a summary page, because I also forgot to give you the symbol for NOT. So here we have it. We have NOT. NOT is this symbol. And for programming, most languages, they're going to use a tilde to represent the NOT function. Okay? Or, the symbol for OR is, whoops, symbol for OR is this nice curvy base and a pointy top. And there we go. Whoops, we need two inputs. There we are. That's OR. The symbol for a logical OR, we'll talk about the difference between binary ORs and logical ORs later. But the symbol for a logical OR is two pipe symbols. Those are actually two characters. Okay. Now we have our AND. And that is flat base, nice rounded body, and our output there. The symbol for AND is two ampersands. Again, those are two characters. Ampersand, ampersand. Pipe, pipe, and a single tilde character. So that is what we're working with. Now, if I do this right, I can squeeze in some truth tables here. So for our NOT, we're going to have in, out, 0, we have 1, we have 1, we have 0. That's our inverter. Okay. For OR, going to squeeze it in here. So we have B, we have A, we have out. We're going to go 0, 0, 0, 1, 1, 0, 1, 1. Running out of room, but it'll fit. Okay, so for OR, if you remember, 0 or 0, well, I'm going to have a 0. 0 or 1, I've got a 1, and a 1, and I've got a 1. So now here comes the AND. AND is got a lot in common with OR, actually. We'll go B, A, 0, 0, 0, 1, 1, 0, 1, 1. and is 0. Oops. So and 0 and 0 is a 0. 0 and 1 is a 0. 1 and 0, 0, 0. So we only have a 1 here. Now there's a similarity here in that, well, that guy and that guy, they're both the same. But these are different. So the and requires both to be true. The or requires any of them to be true. Now I'll throw another gate at you just for good measure. This is the XOR, and it's an advanced gate. So I didn't talk about it before. And in fact, well, no, there is actually a programming symbol for the XOR. So this is going to be, it's very similar to an OR gate, but it's a double bar. So we have our OR gate here, but then we have this extra line here. And that extra line is denoting that this is exclusive. The symbol for XOR is often, but not always, it's often a caret. And the truth table, let's get it in over here. So we have, to write a little smaller, I guess. Okay. We have 0, 0, 0, 1, 1, 0, 1, 1. B, A, out. Okay. Now, XOR is very much like an OR, and it's different from an AND. So it's exclusive, meaning that 0 or 0 still gives us a 0. 0 or 1, 0 XOR 1. I should have said 0 XOR 0. Okay, 0 XOR 1 gives us a 1. 1 XOR 0 gives us a 1. But 1 XOR 1, that gives us a 0. Because it's exclusive. It's saying that it does care if it has two things, and it doesn't accept two things. It's going to be exclusive about it. It won't allow two things to be true. It only wants one thing to be true out of its choices. Now, if you look at this, and you compare that result with the AND, also with the OR, you'll see how these gates differ. And maybe that will even give you a clue about how you create an XOR from the combination of an OR and an AND and a NOT. So, all right, that's it for this lesson. And so everything inside of a computer is made up of these fundamental components. It's really astonishing. And you think, well, how come something so simple can create something so complicated? Well, the answer is that we take millions of simple things and we hook them together, and it becomes a very complicated thing. But fundamentally, computers really are very simple. This is all there is to it. It's just these functions right here will enable you to understand everything else that a computer is doing. Now there's a couple of things computers do that don't quite fall into this category. For instance, audio has an analog stage to it. There's a couple of things like that. But basically, all of the computation, all of the analysis that a computer does, it all comes down to these gates right here. Okay, well, I had fun. I hope you did too. Hope this was informative. Leave some comments, and I'll see you in the next lesson. Bye.